This is the third video in the module where we're looking at models in R. And as you recall, in the first video we defined our model family and our what a model instance was, defined a sample model, and then defined 200 random models. In the second video we then attached an objective function to say how would we assess the quality of a model. We looked at two, root mean squared and residual sum of squares, and then we used R to evaluate the sample models that we had, the randomly generated models that we had, and pick the top 10 from our list of 200. And so the question, or what we're going to do in this video, is develop a process that could potentially find better solutions based on what we have right now. So let me go over to the R, and what we want to do, that we have our top 10 models, this is where we left off last time, is I want to look at the top 10 models in the W1, W2 space. So we're looking here at the models in the XY space where our model is aligned. But what I'm going to do here is I'm going to plot our top 10 solutions in the W1, W2 space. So let me just do that, and then we'll discuss what this means. Okay, so here we go. Here we are. Let me scroll up here. And so here we have our W1, W2 space, and we've used the point geom to identify our top 10 solutions. So what I'm going to do now is I'm going to grab, let me see if I can grab this guy and then copy this in. I'm going to use this in OneNote. So let's copy that, go back in OneNote, find an empty space, maybe right here, and paste it into OneNote. So let me grab a pen here, and when I look, my region of interest in the W1, W2 space is right here. And so you can see all of the values, but these are the ones that are my top 10 solutions. So what I'm going to do now is I'm going to generate some new solution within this space. When we look at where we are in the process, we basically have a couple of options here. One, as I mentioned before, was to just accept the best solution that we have. Another option would be to just generate a whole bunch more random solutions. So we started with 200, why not make 2,000 from the beginning and just sort of replicate the process that we did earlier with more samples. And this is something you should try and see see how that works. But what we're going to do is we're going to look at this attractive space in the W1, W2 space and generate some more solutions within this area. And if I do that, I basically have a couple of options here. The first option I could do is random models in this space. And recall when we made random models before, let me go back to the space we were before, scroll up here, we generated these random models, and so we have explicit control over where we generate. So that we did minus 500,000 to 500,000 and minus 100 to 250. If I look at my space here, it looks like I'm somewhere around minus, I don't know, 275,000, or I guess it's 250 and 500, 300,000 to somewhere around 125,000. So we have a much smaller region in the W1 space. Similarly, we have a smaller region in the W2 space. We're clearly above 0 here. Looks like we're somewhere around 40 up to around 240. So one option that I have is to just use this same mechanism and generate, some number of random observations within this space. And this is definitely something that you should give a try. You should try out. But what we're going to do, because we want to do something different, is I'm going to generate a grid of points within this space, right? So instead of generating random observations, I'm going to generate a grid within this attractive space in the W1, W2 region. So let's see, what do I want to do here? I want to do grid in the attractive region. In my attractive region again, let's say this is minus, minus 300,000 to maybe 125, 130,000. 130,000 in the W1 space. And W2, I'm going to do, let's do 40 to, well, let's make sure that we get them all. So let's do 30. Let's do 30 and let's go up to 280. So minus 300,000 to 130,000, 30 to 280. All right, so back to our studio, and again these numbers change every time because since I did random generation. So here we go. Let's do minus 300,000 to 130. That'll be 13, and then 30 to, what did we say, 280. And so the expand grid function will create a grid based on the two sequences. So I've got two sequences of length 25. This gives me my boundary, and the expand grid is going to create a filled in grid of length 25 times 25. So what's that, 225? So we're generating approximately the same number of points, except this time instead of random W1 and W2, we're putting those within a grid between our attractive region. Also note that I've used the pipe function to call our map double so that we can fill in the points immediately. So when we execute that, we now have a grid data frame. And so our data frame has our W1, W2. Again, this is our grid, and then the corresponding distances. So now I can view these again in the parameter space. So let's do that. Let's view these in the parameter space. And so now you can see here's our new parameter space, which you can clearly see that we've generated the grid points because everything is aligned perfectly. And here is our new attractive region. And now let's go back and plot these values against our sample points. So again, this time the only difference is we're using grid rather than the data frame. We're using our newly generated points. And so we run, and now our lines, our 10 best lines, look even better. So again, what we did was we looked in the W1, W2 space, found an attractive region, and then generated grid points within that region. So now we're basically at the same point that we were when we generated our first random samples. We can stop or we can continue this process. And so let's just do one more refinement. Right, so let's go back and look. Let's go back and look at our grid space here. So just scroll back up and look at the models in the grid space. Run those. And this time, let's look one more time within this basic region right here. And so if you look here, we're at minus 100,000 to, let's see, minus 100,000 to 50,000 in the W1 space, minus, let me write this down, minus 100,000, 50,000. And in the W1 space, we're at 100 to, what does this look like, 150, 170? Let's do 180. So we are doing, well, let's do 100 to 180 in that space. And so let's go back in and regenerate the grid. So if we go back, one more grid. So let me fix these points. So we got minus 100,000 to 50,000. That didn't change. And this time we want to go 100,000 to 180 and generate the same number of grid points, 180. And then again, we're using the mutate to go ahead and fill in the distance values. So we run, and now we go back. Let's go back and look at the grid space. So go back and look at these in the grid space right here. Run. Oops, I looked at the wrong one. I looked at XY. And I scrolled up too far because I'm still looking at XY there. So let me go back down here. I want to look in, there's my models. I don't want to look at models. Scrolled up too far. There we go. Finally, I want to look in the grid space. So there we are, and now here's our new attractive region, and you can see that we've compressed both axes quite a bit. If you go back in the video, we've compressed both of these axes quite a bit. And so now when we run, we see even a tighter clustering of good solutions. Now, we could continue doing this, right? So we could go back to our grid space and further refine, or we could take that same grid space and generate some random solutions, and we can continue this process until we're satisfied. We could also automate the process. So what we're doing is looking at the boundary points, the lowest and the smallest and largest values of W1 and W2 to generate this, what we're calling the attractive region. So we could easily automate this process. The point being that we can continue. We now have a process where we're systematically improving our solution. At some point we will just stop and say, okay, our solution is good enough. Because remember, we're not after the perfect solution, because we are never going to know that true relationship between x and y, because we just have this sample value. So you look at the relative difference between these values and it's probably pretty small. Nevertheless, we could continue the process to get as close as we'd like to get for the given problem. So two final things I want to demonstrate in this video. One of them is the Optimum function. At this point, we could use the Optimum function, which does a search similar to what we've done, except it does automate the process. And so we're calling the Optimum function, and we're basically giving it starting points for the two parameters, w and w1, and then we're giving it the function to measure the distance, and we're giving it the data frame. And so if I just execute that and then report best parameters, best pars the parameters, you can see that the best parameters that it found are negative 22,595 for the intercept and 141.03 for the slope parameter. So again, it's not important how the Optimum function works. That's the subject for another complete video. But just be aware that what it does is it takes the function and uses a search mechanism very similar to what we did to come up with a good solution. Another option that we could do in this particular case is we could use the LM function. And so the LM function says fit the best linear model. So if we run that and run the summary, which displays the summary of the model, you can see here are two parameters. It's got an intercept of minus 22,703 and a slope function of 141. And so this is very close to what we saw in using our Optimum function. Now what the LM function does is finds the true optimal given the structure of the problem. And so when we compare these three methods, our method, which was a more or less manual search method, with the Optimum method, with the LM method finds the true optimal, but it finds the true optimal for a linear function, a slope-intercept line function, or what's a linear regression function. The Optimum function will do a search method for given any type of function that you provide it. And if you look at our process and look back to the code that we wrote, we didn't really make any assumptions about linearity. We didn't make any assumptions about how the distance metric is computed. We simply had a function. We simply passed a function value. So basically our method and the Optimum method will basically work in any case where I can describe the distance, or write a function for the distance. If I can do that, then the method that we used will work. So it's in fact much more general than the LM method. However, the LM method is guaranteed to give optimal solution. So in this case, there's no right or wrong answer. It's just a matter of what the problem that we're trying to solve and what the solution methodology gives us. And so again, I would note that our methodology and then the automated version using the Optimum function is extremely general. It won't always perform this well because we have a very well-behaved problem, but the methodology in general is sound and robust across a wide variety of distance metrics. So back to our module objectives. What we did in this module across 3 videos is define and discuss the concepts of a model family and model instances. In our case, our model family was a simple linear function of 2 parameters, an intercept and a slope. And model instances we created by giving values to those 2 parameters. We then illustrated a simple search-based procedure where we identified good instances using R. So we started out with a random select. We randomly created a set of models. We then applied a distance function and picked off the top 10. We then used a method where we looked in the parameter space to identify what seems like an attractive region in parameter space, and then we generated additional solutions using a grid search. So again, this is a very general search process. It worked well in our case because we have a nice, well-behaved objective function. It doesn't always work this well, but the general process works quite well in general.